Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. The first recursive sort that we're going to talk about is merge sort. Now, of course, all the sorts that we did previously we could have implemented in a recursive way, but there isn't necessarily a huge advantage to doing so. In the case of merge sort and the other sort that we'll talk about, quick sort, there really is an advantage to writing them recursively. The code is much simpler when we do that. So in the case of merge sort, the way the algorithm works is we take whatever array we have and we split it in half. And then we take each of those and we split them in half, and we take each of those and we split them in half, and we take each of those and we split them in half, until we get down to our base case of we have one element. And then we take those elements and we build them back up. And so I'm just going to kind of walk through that. Paste. There we go. With the data that we have here. Well, so I'll start with this side. So the way the recursion works, of course, one side gets called before the other side does. So this has 9 elements. So the index is 0 and to 8. And so we would wind up with a midpoint of 4. I'm going to go from the low end up to that index minus 1. And we'd get an array that looks like this. And then when we split this in half, it would make a recursive call right there. And then, of course, when we split this in half, we get just a 5 and the 3. Now what happens next is, as this pops back up the call stack, it gets back this array that has just a single element of 5 and this array that has a single element of 3, and it merges them back up into the original array. Now the merge operation is done in an efficient way, so that it only looks at the elements that need to be looked at. And so it looks here, it compares the 5 to 3, says the 3 is smaller, so the 3 gets put there, and then the 5 winds up being put there, and we get a merged array that has the sorted values. Then we come and we do our recursion on the other half, and it terminates with the 9, whoops, and the 6. And of course, when these get merged, the 6 winds up going there, and the 9 winds up going there. Now those were pretty wimpy little merges, but now we have 3, 5, and 6, 9, and we want to merge those into this array here. And when we merge these, the thing about the merge sort is, I start off, I only have to look at the 3 and the 6. I know that the first element can't be the 5 or the 9 because these things are in sorted order. So the 3 is less than the 6, so the 3 goes there. Now I'm comparing the 5 and the 6. Well, the 5 is also less than the 6, so the 5 goes there. Now I've run out of elements here, which means that basically I just copy those elements up into there. Now I have to work on the other half. And so I have this, and when I divide it in half, I get that. And then this, I won't bother going ahead and drawing the individual elements. It recurses down to the individual elements, and they come back, and we merge them into 1 and 2. Then we recurse on this half, and it splits with just the 7 going down to one side and the 8 and 4 coming on the other. The 8 and 4 gets split when they merge back up. Of course, the 4 comes before the 8, and then the 7 merges with the 4 and 8, so it compares the 7 to the 4. The 4 is smaller, so the 4 goes there, compares the 7 and the 8. The 7 is smaller, so it goes there, and the 8 winds up being at the end. Then we merge this set of 2 with that set of 3. It compares the 1 and the 4. The 1 is less. The 2 is less than the 4. So the 2 goes there, and then we've spent one side of the recursion. And I keep saying array. Turns out we're going to write this actually with a list. So now I have these two, and I need to merge them up into the full array slash list up here. So I'm comparing the 1 and the 3. The 1 is smaller, so the 1 moves up. Then I'm comparing the 3 and the 2. The 2 is smaller, so the 2 moves up. Now I'm comparing the 3 and the 4. Notice that this is the thing about the merge sort. I only have to compare the next element of each list because I know that each one is in sorted order. And then the 4 is smaller than the 5, and then the 5 is smaller than the 7, and the 6 is smaller than the 7, and the 7 is smaller than the 9, so it would be put up in there, and the 8 is smaller than 9, so it would be put up there, and finally the 9 would come here at the end, and we would get something that's fully sorted. We're going to implement this on a list for one reason. The merge sort has one major drawback, and that is the fact that it can't happen in place. So with the previous sorts that we've written, we could take a single array, we passed it in, and we sorted the values inside of that array. That doesn't work for the merge sort. It's impossible to take, if this were one big array and we had just split it in half and we were just moving things around, it's impossible to take these two and merge them into a single one using only one array, because moving the 1 into the location where the 3 would be messes up the whole ordering, and so we really can't do it that way. So that's the drawback of a merge sort. The advantage of the merge sort is it always divides perfectly in two, and you should remember from our discussions of binary search, when you keep dividing perfectly in two, the number of levels that you have in your division is log base 2 of n. So we have log 2 of n levels, and at each level, because every time we did a comparison we moved something up, you know that you only have to do order n comparisons and order n moves. So merge sort is in log n. It's in log n when you give it really bad data. It's in log n if you give it really good data. It does in log n comparisons. It does in log n memory moves. It's very stable with in log n work, but it can't do it in place. So it winds up using a little bit of extra memory, and it turns out that if you're going to use some extra memory, you might as well do it with a list. So let's look at how we would write this in code. So I'm going to define our merge sort, and we're going to pass in a list of integers here that we're going to sort, and because it's a list and we can't mutate it, we need to give back a list of integers. Okay. And so the way that this works is we want to, so if lst.length, by the way I'm writing this is not necessarily the most efficient way. We just want to see how this works. I could make changes, and definitely for the quicksort we're going to do next, we're going to write it in a fairly inefficient way, but we're going to write it in a fairly inefficient way that is very easy for us to write. So if the length is less than 2, well, then I just return lst. If it's not, then what I have to do is I have to split it down the middle. So let's go ahead and let's create two vals for a, how about we call it begin and end, or first and second. And those will be equal to lst.split at lst.length over 2. Okay. Remember, the split at breaks the list into two pieces that split at that index. That index itself winds up being in the second half, and everything before that index is in the first half. Then I want to do my recursion. I'm going to call merge sort on first, And now this gives me back a new value, and I also need to call it on the second. And I want to take those two and I want to merge them together. So I want to merge the results of calling merge sort on the first half and the second half. Okay? Simple enough. I just need a definition of merge here. So let's go ahead and let's def our merge. And merge is going to take a, how about we just call it A is a list of ints, and B is a list of ints, and it is supposed to give us back a list of ints. And I'm going to write this one using pattern matching. So I'm going to match on the tuple A and B, because it turns out the merge works very nicely with the pattern matching. So one case is that there is nothing for A, okay? In which case, well, if we have no A and I'm merging them, I just want to give you back B. Another option is there is an A, but B is empty, in which case, when I merge them, I just get the A. If we're not in one of those two cases, then I want to do a pattern y cons y's. So here I'm doing a head and tail pattern. So for the A list, I take the head of A and the tail of A, and that's our x's, and then the head of B and the tail of B is our y and ys. And I have two possibilities. So if x is less than y, then what I'm going to return is x const onto the result of doing a merge, I don't need parentheses there, a merge of xs and b. Else, if it's not less, I'm going to do y, and let's make this less than equal to, technically so it's stable, y const onto a merge of a and ys. Okay, now let's test this. So val nums equals list dot fill. Let's make 10 numbers. Util dot random dot next int. We'll pull numbers, random numbers out of 100. Print line nums dot mk string. We'll put them together with commas between them. And then, instead of doing just nums, we'll do merge sort of nums. And let's see how close that is to being correct. Wow, it compiled. And not only did it compile, look at, oh wait, nope, no. This is, so here we have our original numbers. They are clearly out of order. And then 11, 17, 20, 24, 24. So we had a tie there, but that's perfectly fine. 41, 56, 60, 86, and 93. Let's run it again. 9, 26, 29, 43. Indeed, there we go. Those values are in sorted order. Okay, so you can see how the merge sort works. On the way down the recursion, all it does is that it does a split, and then it does the recursive call on the left half and the right half. And then it does another split on each of those, and it does the recursive call and split and recursive call and split and recursive call until you get down to a list that has one element in it, in which case we just return that back up, and waiting on the call stack are a whole bunch of merges. And so the merges pull these off right here. Well, this was easy to write, and in many ways it's nice, beautiful, functional code. There is one minor problem with this. If I were to make this array really large, this would crash, because it turns out that this right here is not tail recursive, and so we can overflow the stack if we use this particular version of our merge sort. We'll write a better version of merge sort in a later chapter in the second half of the book, but for now, this is sufficient to show you how this particular sort works. And remember, the big thing is, whereas all of our previous sorts were order n squared, this sort is order n log n. And you should remember from the binary search that that whole log n grows much, much slower than n for very big numbers. So whereas order n squared can literally become intractable once you hit, say, anywhere from 100,000 to 1,000,000 elements, you'll start to see it slow down around 100,000. By the time you get to 1,000,000 or 10 million elements, you can't wait for a bubble sort or even an insertion sort to work. But it turns out the merge sort, if in this case it weren't for the fact that the stack would overflow, would be perfectly happy working on something that has 10 million elements in it. That would not time out. So that's it for our merge sort, and we'll come back in the next video and we will write a quick sort.